Question 2, you need to use Q times V or Q times delta V, half mv squared. That's one way of doing it. There's another way. But again, it is the difference. If they're releasing the electron from the center, you need to get that difference, delta V. That's question 2. Question 3. So question 3, you had used right-hand slap rule. For the electron coming into the magnetic field is into the board. If the electron is coming that way, it's going to experience a force. That force will become a centripetal force. So if you want to find the radius will be given by this equation. If you guys forgot how to use the right-hand slap rule, you had to point the thumb in the direction opposite. This is the right hand, opposite to the electron motion. And then your finger should be pointing in the direction of the magnetic field. Something like that. It's not the best drawing. You can see the force down. Something like this. And then question number 4. Step down means step down, the voltage goes up, down, the current goes up, P stays constant, power stays constant because it's ideal. Question 5. Identify the device. If it is a motor, there should be a battery. If there is no battery, power supply at the end, that's the generator. If you have a split ring commutator, that's something to do with the DC. Question 6. We're going through the NEEP multiple choice question. Once you've done that, we just go back to light and matter. We need to go through de Broglie's explanation, maybe some energy level diagrams, and then revisit back to the NEEP paper. When they ask you to find the tension, we need to find, so the acceleration is that. So mass times acceleration, you need to find need A. If that is M1, if that is M2, the driving force is M1. So you can find the acceleration by your F net, which is M1G divided by M1 plus M2. Once you find that, just submitting question 7. Now, relativistic mass is given by the gamma times rest mass. The mass energy is given by mc square. So in the question they're giving the m naught c squared, so you can figure it out. Question 8. That's conservation of energy. Spring potential energy, same as the change in kinetic energy. If you can find the kinetic energy, that's the work done by the spring. Find the K value and check the gradient. Matches. Question 10. This is, we had to assume both ends fixed because one side is, although you have hand, you're holding it. The lowest frequency is they're asking, but the nth frequency given by NV on 2L. The lowest frequency is going to be N equals 1, 2, and 3. That's question 10. Question 11, 12, we don't need to worry about. You can skip those questions. Now keep in mind, in imaging, diffraction makes images blurry. Diffraction makes images blurry. Because when they start to form, the rings around the object that you are watching, you can't get a clear image out of that. The de Broglie wavelength of electrons are way smaller than the optical, the visible light. Way smaller. Way smaller than visible light. Therefore, the diffraction effects comes very late when you're looking at very small objects, and diffraction effects comes in. But otherwise, you can get a clear image because lambda and W ratio is very small. Therefore, less diffraction with electrons. If you guys can note it down or just look through. So we're going through, people who are just joining in, we're just going through the NEEP 2018 multiple choice questions. You can skip those questions. These questions are the one taken off this year's study design. But you can just give a guide. I haven't given the answer, exact answer, just give a guide. What's happening? Why Monaco? Hello? You didn't get the link or? No, I didn't get the link. Oh no, okay, I'll send you. Oh, Okay. Just be people. Can you get the link? Sorry. What's this saying? Because the hand, and also because we need to rely on, because if it is a free end, it purely should be a really free end for that point to move around. Because here the hand is more like a vibration that it produces the wave there. If it is purely a free end, it's like a no interruption, it can move by its own accord. But if you have a hand and if you're moving up and down, it's not the wave that's producing that up and down motion. It's more like your vibration that what you're producing. And also, yeah, okay. Sorry, Manik. So we're just going through 2018 NEEP paper, just going through the multiple choice questions very quickly. So you can skip those questions and then give it a try the others. I just give like a guide how to do these questions. Okay, that's question 13. Question 14. Check sometimes I don't see this. Let's check with the Vidru got it or not. Okay. Once you get that, that's question 13. Question 14, should I write? Maybe I'll get it off step down. Can you guys know that one? Question 14, just use C equals F lambda. So you know visible region. It is violet here, red there. That's about 350 roughly nanometers. That's red, about 700. And ultraviolet here, it's shorter. 15, 16 you can avoid. 17, fringe spacing, lambda on D. Lambda on D, fringe spacing. Question 19. Yeah, question 19, although you're talking about a refractive index, just ignore that, but just treat like uncertainty question. Question 19, guys, they're talking about a prac you've done on refractive index. It's not the science behind it what matters. I mean, science, it is science as well. It is the uncertainty. It is an uncertainty question. So just treat that as an uncertainty question, then try to do that. Question 18. The energy of photons, if they have the same wavelength, same momentum, lambda of electron, they have the same momentum. The energies are different, but energy of X-rays are always bigger. They're greater than energy of electrons. Okay, they're bigger than energy of electrons. So should I be going through this NEEP exam 2018, NEEP exam? So we're just going through the multiple choice questions. You can skip those questions. I just give a little bit of a help here and there how to do these questions. Just want to give a quick try as quickly as possible. I'll remove the, if you can make a screenshot, people who just came in, just take a screenshot. I'm going to delete the site and remove this side. Take a screenshot, keep it on the side in your screen, and then I'm going to wipe this part. Take a screenshot and go to wipe it. So question 19. Question 19. So Vidro, we just going through the NEEP exam multiple choice questions. Once we've done that, we'll come back to light and matter. So you can skip those questions. I just give a little bit of help here and there. I think I got rid of question 1 and 2. Question 3 onwards, the help is still there. Question 3 is there. Question, I don't know where question 4 was. Should be somewhere. I think question 4 is a step down transform. I can't remove it. 5. And then 6, 7, 8 here. 6, 7, 8, 9, 10. So I'm going to give a bit of a help here. Question 19. The definition of error is the difference between the accepted and measured. Accepted. So say for example, your expected value for G, say 9.81. So this is the accepted value. The measured value, say 10.3 or something, maybe just make it 10.3 meters per second squared. So your error is the difference. Uncertainty is the range. It's the range of value you get in the measurement. You obtain in the measurement. Say for an example, you got a value 10.3 plus or minus 0.5. Then your answer can vary between 9.7, take over here. So 9.8 and 10.8. If I take 0.5, that's 10, yeah, 9.8. So it can vary between 9.8 and 10.8. That's the range. I'm taking 0.5 out and adding 0.5. That's the range. Range of values that you can have. Okay, I'm going to remove this right-hand slab rule part. If you guys can take a screenshot very quickly. Then we'll come back to the energy level diagrams. Question 20. People who finish these multiple choice questions, just go to short answer. Start from question 1. Question 20. Now, this is the definition of precision and accuracy. Okay. So precision means your variation in your data is very small, that not necessarily close to the expected value. Say your data is hitting somewhere, but they have a very small range of variation. So this set of data, the precision is very high, highly precise, but not accurate. Why I'm saying that is not close to the target, highly precise, but the one here, they're not precise, but they're accurate, close to the target. They are accurate, but not precise. Because the variation is too much. If you guys finish this, let me know. Just quickly give a mark. Yeah, so if you get 5 out of 16, 10 out of 16, 16 out of 16, but I would like to know, just give an indication where you are now. Done? Y is answer to 17B. Okay. Yeah, that's wrong. Don't look at it. There are some wrong answers there. Okay. So the answers question 17 should be A, not B. There are more errors in this solution. Be careful. I'll put the answers here. If you guys want to go through any of the questions, I can quickly go through it. Okay, so you got 15, that's good. Question 18. What was question 18? Yeah, they have the same momentum. The photon has more energy. You can just prove that this is a photon, like say X-ray, is PC. That's the electron, P squared on 2m. I can sub it in P from that. So your electron energy is the energy of a photon divided by 2mc squared. You can put a value saying energy of X-rays is, I don't know, just say 200 electron volt and calculate what's the energy of electron. You can see energy of electron is far lesser, even sometimes 100 times lesser. Question 13. You got 13. Okay, that's good to start with. It's not a bad thing to start with. Anyone got below 10? That's where I just want to have a feel. Be honest, guys. I'm just trying to help you out, not to judge you or anything. If you're getting below 10, okay, Pathum's good. But if you get below 10, I'm not telling your name, but I just want to know. Don't feel bad. I need to know because I'm here to help. Okay, guys. Okay, that's okay. To start with. When you're doing practice exams yourself, if you get 80 to first couple of papers, that's fine. But remember, you have to improve. To get 40, you need to get close to 90%. Okay, that's good. I think there were 16 questions in it. Okay, yeah. That's right, that's fine. Oh, yeah. Okay, that's good. Which one was that? Okay. Okay, let's move on, yeah? I like to see Shuka, Dinura, Rehan. You guys, if you guys can let me know how, like, be honest, guys, because this is not a judging exercise. This is just a helping out exercise. Need to know. If you done badly, that you done badly. So we need to know. That's all. Okay. Yeah. You're good. Okay. What do you get? All right. Oh, yeah. Okay, excellent. Okay. All right, we'll move on. Now, now you guys have your practice exam coming up in first week, right after school holidays? Trial exams, Ramadhu and Sudesh.
Yeah, I think so.
Yeah. They stand like they're giving like a standard paper every year, so maybe go probably go through that. In the school holidays, that's okay. I have mine. Okay. Mostly they're giving either NEEP or STAV or probably, yeah, don't know. Could be anything. TSSN. All right, just move on to finish it off the light and matter part. I'll get rid of this. Some people might not have managed to finish it. Hey guys, remember question 17, the answer should be A. The solution says B, that's wrong. It has to be A. Question 17, answer has to be A, not B. B is wrong. Question 17. Okay, we talk about energy level diagrams and then de Broglie's explanation. Now you guys remember from last week, Bohr model of atomic structure. And based on that, he came up with the idea because he was saying electrons are orbiting around this well-defined path. And one thing that he said that because there was a discrepancy in his model, the discrepancy was his model could not explain that well how the electron can survive without collapsing into the nucleus, because they knew that accelerating electron should lose energy. So he brought like a semi-classical it's more mathematical. They said that there was a complaint said that he was bringing maths to justify his answer. So his mathematical relationship was we call angular momentum, linear momentum of this electron times by the radius. So he said that if it follow a multiple number of Planck constants, we put 2 pi, h1 2 pi, then electron can sustain. But there was no clear reasoning for that. So based on that, he came up with these energy level diagrams. Where are the lowest energy levels? So these n values are the ground state, first excited state, second excited state, and so on. Okay, that's n equals 1 ground state. As I said, they can give you the ground state from 0 to higher positive value, or start with the most negative value and go on. So that's ionization. And n equals 2 and so on. Most of the elements, most of the gases, the gap getting smaller and smaller, but you can see mercury, there is a big anomalies like it's getting smaller and then suddenly there's a little bit of an increase and then again smaller. So these electrons can absorb energy by external photon, provided you supply an exact amount of energy. If that energy matches between two energy levels, hey guys, when you're drawing the absorption, always the arrow goes up. Absorption, if they ask you to represent absorption, the arrow should be upward. You can't have an arrow stopping in the middle. You can't have that. It has to reach to the other energy level. You can see electrons are allowed only these discrete energies levels, what we call quantized energy levels. So that's the reason that Niels Bohr bringing in is this idea, mathematical relationship, to explain that. So whenever electron excited into a higher level, it can come down by releasing that excess energy, either that, or either that, either that. So you can have 3 emission lines corresponding to 1 absorption line. Okay, we'll get through some questions. That's the easiest way to handle these energy level diagrams. Sometimes you had to do a bit of a trial and error working out. Can you guys find, I think I gave some questions last week as well. If you can find that worksheet in it, we'll finish that and we'll revisit back to the light and matter. Okay, no problem. Okay. So the first question, in example 1. So this is the energy level diagram of mercury. So this is the ground state, 0 eV, this n equals 1. We call the ground state. And then you have 4.9 next energy level, n equals 2, 6.7 eV, n equals 3, 8.8 EV, N equals 4, and so on. And that's the ionization. When it reaches there, it's never come back. 10.4 or above, it will absorb and leave. The first question, which one or more of the following photon energies can be emitted by the mercury atom in the second excited? That's the first excited state. That's the second excited state. If the mercury atom is there, when it's emitting, it can emit 3 lines. That's one. That's the second one. That's the third one. Three possible emission lines are The first one would be N equals 3 to ground state. In terms of energy difference, they are 6.7. For the second one, N equals 3, N equals 2. That would be 1.8, that's 6.7, 4.9. The third one, N equals 2, 2N equals 1. That's going to be 4.9. Now look at your answers and pick the right answer. So you have 4.9 there. And then there is no 8.8. There is no 2.1. 1.8 is there. The answers are B and D. B and D. I don't know how Nihindu and Isuka went, yeah. And then Tinaru didn't want to tell me. He said everything's fine. Okay. Example 2. Mercury atom is initially at second excited state, and then from second to third. So this is the ground, first, second, is going from second to third. Look at the energy difference between these two. So absorption means it's going upward. Don't put 2 arrows, just one head. The energy difference is between third and second one. 8.8. Take away 6.7. 2 point something. 1.8 plus 2.1 EV. 2.1. So answer C. Just skip question 3 for the time being. Once you go through de Broglie's explanation, we'll come back to that. Example 4. They're talking about emission line. Emission line should be coming down, not going up. And the energy difference should match up with the value they say. So you can see only possible one would be A. All the others are not possible. You can't have in between. You can't have lines in between. So that's give you energy difference of 1.65. That's the answer is A. You guys want to give it a try, this question 5, and tell me what answers you get? Question 5, example 5. Okay. Example 5. Okay, I get some numbers now. Okay, go through example 5 and tell me what would be the best answers you get. I'll give you like 2 minutes. Question example 5, anyone minute to get the answers? That's one of the answers. There are 2 answers. Yeah, that's correct. It's not B. A is the one of the answers. We're giving a range of wavelength shining onto this gas here. That's 4.9, 6.7, 8.8. That's ionization. If the electron reaches there, it's never going to come back. So electron in the ground state can excite it to either that, or completely ionize. So electron in the ground state either 4.9, 6.7, 8.8, or 10 O plus, 10 O more. On the other hand, that's in the ground state. Then there is electron in the first excited state. Electron in the first excited state can absorb that, or go back to the ionization. First excited state, it can absorb the difference, yeah? It can absorb 6.7, take away 4.9, 1.8. It can absorb 1.8. Or it can absorb 8.8, 4.9, say 5, 3.8, 3.9. Or it can absorb 5.1 or more. Then it ionize. That's just ionize. Now look at the range of your range 1. 200 to 300. just quickly check what energy range that you are giving. So if we look at the energy range, let's see on lambda. So it's giving from 6.21, should be smaller. And it's giving basically 4.14 to 6.21. See whether anything is matching. Yeah, that matches. So it should be giving. It can absorb. None of these ones. The next range, 500 to 690, 695. Energy range. It's not chopping off, cutting off. 4.14 negative 15 by 8 divided by negative 9. You get 2.48. 2 times by 500 negative 9 divided by 695. You get like 1.79 EV. That's the range it's giving. Yeah, so this is possible because at the edge is going increasing. That's possible. 3.9 energy is not giving either any of that. That's not possible. 5.1 should be possible from that first one. It is quite possible, but you need to see whether it's within your answers. So you have 1.8, yes, that's good. 2.1 is not in our list. 4.9 is in our list. 6.7 is not in our list. 8 point, that's not possible. So A and C. A and C are the possible ones. Okay, A and C are the possible ones. Okay. So the question 6, think about question 6, electric energy to raise the hydrogen atom to the first excited state. That's the ground. From ground to the first excited state. They say the difference is 10.2. And to ionize it, you need 13.6. The question is, if you supply 14.8, definitely it will absorb that and ionize. It will definitely ionize because it's more than ionization. Ionization is 13.6. You supply 14.2. The remainder, so the kinetic energy of the object, the electron, it's a difference. We supply 14.8, 13.6. The difference is like 1.2. That's kinetic energy. You just escape completely with the kinetic energy of 1.2. The one in the ground state. So the answer should be C. Okay, we'll hang on to that. We'll go through the de Broglie's explanation and then we'll wrap up everything. De Broglie's explanation of presence of the quantized energy levels. He was trying to give an explanation why the electron can't collapse. This is a common exam question, okay? It's the presence of quantized energy levels. Remember that energy levels were not continuous, they are discrete. Here one, here one, here one, you can't have in between. So he's essentially giving a better explanation how the electrons can go around in a circular path without losing any energy. It gives ionization energy is 13.6 Joule in the previous question, because it says the ionization of hydrogen is 13.6. Okay. Now, he was saying that only way that electron can sustain without losing energy on a particular orbit is by bringing the wave nature of electrons. He's saying that electrons are particles, but they have wave properties. Okay, so remember this exam question. Stated that electrons are particles, however, they show wave behavior. That's 1 mark. You need to state that electrons are particles, but they show wave. That's one of the keywords. They show wave behavior. What he was saying, like you guys remember standing waves, technically, if I form a standing wave on a string, assuming there is no interaction with the air molecules for the string, there is no other interaction with the surrounding materials like guitar string, we can't avoid it interacting with the air molecules as well as the box of the guitar through the plate. Otherwise, if you assume they isolate all that, if I start to produce that standing wave, the standing wave should reinforce each other. And then technically there shouldn't be any energy loss. The standing wave should go forever. We know in practice it's not happening. But if there is no any other interaction, it should go forever. The amplitude should maintain continuously. So he's bringing that idea. He was saying that, okay, only way that electron can sustain, occupy and sustain in energy level, they should produce standing waves because they are waves. So for electrons, to occupy and sustain in a certain energy level, essentially without losing any energy, they should form standing waves. They should form standing waves. So that's another keyword, that forming standing waves should be included. Should forming standing waves, that's another keyword. The next thing is to form standing waves. In order to form standing waves, the circumference should be large enough should be sufficient to accommodate whole number of full wavelengths. Or integral number of wavelengths. Whole number of wavelengths. Say 2 pi r is the circumference, has to be satisfy this condition. 2 pi r equals n lambda, where n equals, these are whole numbers, 1, 2, 3, 4, and so on. I'll just jump in. I just want to try to explain something. Can you remember that Niels Bohr's relationship? This is what Niels Bohr said. Niels Bohr said that in order for electrons to keep going on a circular orbit or to occupy and keep going, he said that angular momentum has to be a multiple number of Planck constants. Maybe he looked at that and then he's bringing his wave model. Once you bring the wave model, have a look. If I introduce de Broglie wavelength, H on mv, I can say mv equals H on lambda. So if I replace that, this is coming from Bohr model, okay? This is nothing to do with the de Broglie, this is the Bohr model. Now, because de Broglie said that electron is a wave, if you bring that, and then if I replace that mv with H on lambda, that cancel. What do you get? You get that relationship. But you don't need to know. I'm just saying that it's very interesting that you brought that once you introduce that wave model. So you can just justify this equation. So this is another point. Like definitely you need to include that. In your explanation, you have to include that. Okay? And then you have to say that so larger the radius. When you go for larger radius, the n number increases. To greater the n value. Only particular wavelength can satisfy this condition. Therefore, the lambda is linked to the energy. we cannot just purely get the kinetic energy itself. We need to consider electric potential energy as well. But we can see it's related to the wavelength. So only specific energy levels are allowed to occupy. Around the nucleus. You can see that it's not a really a well-defined path, it's a probability, like it's a wave now. So allowed to occupy. So this is the reason for the presence of specific energy levels or quantized energy levels. Okay. Now, just to understand how you sometimes they will ask you to draw the standing waves. Around the circumference. So this is n equals 2 means this is the first excited state. So you should need to fit 2 whole wavelengths. 2 whole lambdas. If I get the circle, divide the circle into 4 parts. Into 4. Because there are 4 nodes there. There are 4 nodes. You done that? That's half a wavelength. That's 1 full wavelength. That's 3/4. That's another wavelength. And then you can draw your standing wave around. You can get rid of it or maybe just keep like a broken line in the center because there is no electrons are not moving there. That's n equals 2. You can see just 1 node, 2, 3, 4. If they give the diagram and ask you to find which energy level, you can count the nodes and divide by 2. Divide by 2. That will give you the n value. Or you can just count the bumps 1, 2, 3, 4 and then divide by 2. That's works as well. Okay, n equals 3. I think you guys know how to draw this here. N equals 3, divide to 6. You can draw like your Mercedes-Benz mark or piece mark and then divide further and then draw it. There are 6 nodes. Get rid of these ones. Yep. So n equals 1 is a bit difficult, but you can still do it. N equals 1, divide to 2. You can't have n equals 0, okay? I think last year one of the schools said n equals 0. You can't have n equals 0. That's it. Now, if the circumference is insufficient, you can draw one saying that it's not allowed as well. Like just draw a circle somewhere. Let's say there's a particular circumference we are checking whether you can produce. Just show that it's crashing. That's all you need to show. It can't produce, not allowed. Just crash in there. All right. You can just quickly look at that question that we skipped and then get the answer, and then we'll move back to neat paper. Any question, guys, with this? But there's a big chance you can ask to explain this. Presence of discrete energy levels. Since they've taken off more questions from waves, they can ask it. Hey guys, on this, can you look at question 3, example 3, and tell me what's your answer? Example 3. They ask him which one producing 4 wavelengths. I didn't previously show that. That's one of the one wavelength between two. It's not two adjacent. There's one wavelength. You should see that 3 wavelengths there. Yeah. It's easy to recognize. So they say 4 wavelengths. 4 wavelengths is going to be, answer is C. Answer is C. Okay guys, now in the practice exam, should we do light and matter questions, or what do you think? Or we should be go through in the order? Anyone have any preference? Maybe if you want in order, please. Okay. Okay, just yeah. What do you want? You want to go to light and matter? Okay, because you have a sack. Yeah. Maybe just go to light and matter. As a few people having sack, please. Yeah. That's in question 14. Start with question 14. Start with question 14, just the benefit of people having sack this week. Question 14. When you guys done, I'll just wipe it. Do you guys want to give it a try first? Maybe use a pencil or something. In the exam, that everyone know that you have to write using a pen, blue or black pen, yes? Hopefully you guys know that. People are still using pencil, but when you scan it, sometimes very difficult to see. That's the only problem. I'll be marking papers this year too. So we have this training session on 25th of November. Okay. I'm removing this. If you guys can take a screenshot if you want. Give it a start. So they're saying that the students are doing an experiment. First experiment, when you conducting or when you conducted, you can see you're getting your standard EK max versus frequency graph. You can see how we are not allowed to use dark pencils. People are still using dark pencils as long as it's dark. It's okay. Because I can see like still people are using some light Pencil is so difficult to read. They're not particularly talking about particular name, diffraction pattern. So they're talking about like just diffraction pattern produced. Now remember Davis and Garmer's experiment was like a very primitive. They just accidentally found that. But when G.P. Thomson talking about it, he I think did more detailed experiment, G.P. Thomson. So he went through different materials, different metal, not only metals, he went through like a plastic as well. But they're not particularly talking about any name. So G.P. Thomson mentioning that Davis and Garmer's experiment has some errors as well. Yeah, so that's it. Rings, when you say double slit, that should be like interference pattern, yeah? Yeah, but when you're talking about electron diffraction or X-ray diffraction through double slit, don't mention about Young's name. Just say double slit experiment, because they were a bit annoyed saying, because when you say Young's double slit, they think that Young conducted the experiment. This is like way after Young's experiment, they conducted the double slit experiment with electrons and X-rays. Okay. I'll get rid of that. Yeah, this is, I saw some, yeah. There is the paper. I think I emailed you guys that paper. I don't know, can't find it. Just say that Davis and Garmer's experiment had 30% error or something. And he was using low energy electrons, like 53 EV electrons onto the surface. No. Okay, the question says that, okay, they done the experiment, they got that, they repeated the experiment with double the intensity, that there was no change. So they're asking this, both experiment, how they contradictory to the wave model. So it's a 2-mark question, but you have to say that prediction on wave model. Predicted that the energy of electron or maximum energy. Should be proportional to the intensity. But they said that energy of the light is proportional to the intensity. Proportional to intensity. And not on frequency. The light with any frequency should be able to eject photoelectrons. Eject photoelectrons. Doesn't matter what their wavelength. Regardless of their frequency. But the experiment 1 shows that EK max linearly increasing. With increasing frequency. And no ejection of photoelectrons. I think if you look at the graph below 5.5, so that's the threshold frequency. And the experiment 2 showing that the EK max is independent of the light intensity. Independent of light intensity. So these observations to be a model. Part B. They ask you to find the stopping voltage. Remember EK max, same as Vs in EV. Find the value should be like 2.3. You can read from the graph as well. If you're capable, you can read from the graph too. Okay, tell me your answer for answer C. What page? This is question 14, not page 14. Question 14. The NEEP one. Question 14. The page number, not sure what the page number is. It's a question 14. It is a NEEP one again. Yeah, Shula, this is a NEEP one. Question 14, not page 14. Okay. Sorry, yeah, it's a NEEP paper. We went back to the NEEP one. How do you answer part C, guys? What's the best argument?
Would it decrease the energy of the electrons?
No, I think it's something more than that. Because if you look at the wavelength of the green light, they're giving for some reason. You can do two ways. You can look at the wavelength, longest wavelength that you can produce the photoelectron, yeah? By looking at the threshold frequency. Or, remember that the red has a longer wavelength or lesser energy than green. Red is sitting here. And the green is there. If you can look at what's the frequency of the green light, And then you can compare with the threshold frequency. It's a little bit of it. Just since they're giving green, check the frequency. I think they're purposely giving that frequency matches with that. Frequency matches with the threshold frequency, then obviously the red can't produce any photoelectrons because the wavelength of the red is longer. Longer the wavelength, lesser the energy. So part one, you have to find the frequency of the green, then state that that frequency is at the threshold frequency, then mention the wavelength of red is longer, therefore no ejection of photoelectrons. Or you can say the frequency of red is smaller than the threshold frequency. That makes sense, Vidura?
Yeah.
Yeah, okay. Question, yeah, of course, question 13, yeah. So question part D, finish part D and then there's a request to do question 13. Do part D and then we'll jump to question 13. Question, there are a couple of more on the light and matter. Yeah, okay. We'll do these questions, Sudesh, and then come back to 13, okay? So this is just the light and matter, few people having sex here. Part D. So you try to find the frequency of the green light, C on lambda. Frequency of the green light, that's 3 times 10 to the power 8. And that's 545 nano. I think you get like 5.5, 10 to the power 14. So this is a threshold frequency. The frequency of red is smaller than the green. Therefore, no photoelectrons ejected. No photoelectrons will be ejected. So next part of the question. They say they change the metal in the cathode, replaced by something. So, so this is the original graph. This is 5.5. Now they selecting a different metal. If we shine at 12, this is 10 times the weight, 14. They say the EK max or stopping voltage is 1, somewhere there. So it's a matter of drawing a parallel line, but for a safe device, you can pick another point if you want. If you can find the work function, it's easy to draw that line. So we know Vs, HF minus work function. You can find the work function. Which is 4.14 negative 15, 12 times 10 to the power 14 minus 1. So when you do that, it's become like a 4 or something. Then you pick a point that 4 is another point. And then you can use those points and just draw that straight line, parallel line. So you just draw it like a broken if you want. Okay. Question 15. Question 15. So this is the energy level diagram. They say draw an arrow showing the transition of electron as it absorbed. So it's absorption, so it should be jumping up. So of a photon, the frequency is given. We need to find the energy. So what's the energy corresponding to that? The energy is HF. If you look at the energy, that's about, I think, 2.5. So 2.5, this is 10.8. This is 6.5, so the gap of that is no way 2.5. That's 4. You can see the gap is 2.5. So absorption is going up. You need to show an arrow there. Next thing, explain why electron is able to exist in the energy level negative 6.5. If they mention about a particular energy level, which is n equals 2, don't give that generic 2 pi r equals n lambda. Instead, say that 2 pi r equals 2 lambda, because 2 wavelengths should be wrapping around that whole circumference. So you have to mention why electrons are able to exist. And form standing waves. Two full wavelengths. Around negative 6.5 energy level. Okay, so because 2 pi r, 2 lambda, you can draw it, you can show that. It's n equals 2. That's your nucleus. So positive, maybe something nucleus. N equals 2, that means you need to divide into 4. Because it can form standing waves and satisfy that condition. So it can form, so therefore electrons can be able to occupy. N equals 2, that circumference is sufficient to fit whole wavelengths. Okay, question 16, very quickly. Question 16. So the electron has a mass 9.1 negative 31 kilogram. And it's traveling, the speed is 1% of speed of light. 1% of speed of light means 3 times 10 to the power 8 divided by 100 times 1. 10 to the power 6. So then you can find the de Broglie wavelength, H1 MV. Always remember de Broglie wavelength, you need to use 6.63, negative 34. Hey guys, everyone got that revision booklet for light and matter? The revision booklet for light and matter? When taken low electron diffraction, how diffraction patterns produce evidence. Do we talk about the diffraction? Talk about diffraction. Diffraction, because remember, even the diffraction, the bright and dark bands are produced by constructive destructive interference. But we talk about diffraction purely by looking at, okay, what's the difference between diffraction and interference? So if you think about a single slit, what's really happening? Ultimately, we're saying that it is the spreading of wave from that slit. Because of the spread, the waves are traveling from different locations. That's why we kind of interference and diffraction comes when you explain in the diffraction effect. So the path difference that you produce is what causing that bright and dark bands. But give the prominence to the word diffraction when you have a single slit or maybe a string pattern, but you can use the words constructive and destructive words, interference words, when you're talking about this bright and dark band, because they pass through this grid because of change in the direction, change in the path or the spreading, they're coming here and then going to a different direction. That's why we call it's a diffraction. But ultimately, the production of rings are as a result of the difference in their paths between beam 1 and 2 that contributing to that rings here. But use the word diffraction, but you can use the word constructive and destructive to describe the bands there. Okay. So when you sub the values in 9.11 negative 31, 3 times 10 to the power 6, you should get a value 243 negative 9, which is 243 nanometers. And the last one, part B, just use Q times V half mv squared. And V is the delta V, V is the potential difference. And solve for that. So that should be 25.6 if we solve that. Solve that. Okay. That's another part there. Part C. The paper is 2.5 hours. You feel like big training, but that's the exam time, so you have to be. The question they are asking in an experiment, beam of electrons of de Broglie wavelength 350 is fired at very thin nickel, where the nickel atoms are. So the spacing between the atoms, it's like your W. 0.091 nanometer. And the wavelength 0.350. You can see that over that is bigger than 1. They should be not necessarily need to be bigger than 1 when you're talking about the diffraction produced by X-rays or electrons. Even the values are, as long as in the same order, -9, the other one also -9, kind of same order. They say you can get significant diffraction like 0.2, 0.3 as well for electron and X-rays. But generally we're looking at the value close to 1. What conclusion can be drawn from the data presented regarding behavior of electrons? We need to mention it's a diffraction pattern. The image shows a diffraction pattern, or the figure 20 represents a diffraction pattern. Produced by electron scattering through metal target. So the bright dark fringes rings produced by constructive and destructive interference. Since diffraction is a wave, meaning so this, what they say, what it can conclude that it can be concluded electrons are showing wave behavior. Basically, we're saying that we recognizing the pattern as a diffraction pattern, and then we're describing how the rings are produced, and then we're mentioning that diffraction is very unique to waves. So therefore, we can conclude that the electrons are behaving like waves. So the logical exponent, like saying, so the figure shows represent diffraction, and they'll be talking about these bright dark bands, and then we're saying that diffraction is unique to waves. Therefore, we're concluding electrons are showing wave behavior. Okay, there's another question about light and matter. Part D, it's kind of confusing the way that the question was asking. For your answer to part C, provide explanation for the behavior of electrons. So what they were expecting here, the ratio, lambda on W ratio. So lambda on W ratio is 0.35 and then 0.09, which is about 3.8. So So then you have to say the reason for significant diffraction. Ratio greater or equal to 1. This question, let's have a look, question 13. Okay, so question 13, this is like a wave question. So do you have as a part of the practical investigation, group of physics students are investigating sound as a wave phenomenon. Okay, so they set up the speaker at 20 meters from the wall on the school ground. There are no other walls in the vicinity. They use a signal generator to enable the speaker to emit sound in the direction of the wall. So the sound wave travel and then reflect back, yeah? 4B is a student in the group is going to walk from the speaker along the shortest path to the wall. The student set the signal generator to play a note of wavelength 5 meters from the speaker. Both 4B, before 4B does so, the student group discuss what 4B is expected to hear as she walks from the speaker to the wall. Samantha predicts that 4B will hear a constant intensity throughout her walk. Harold predicts that 4B will hear gradually increasing sound as she walks to the middle of the position. And then she will gradually decrease in sound as she walks in the middle of the thing. Evaluate, according to this thinking, like pretty much both are incorrect, because she should be able to, like, we had to talk about production of the standing wave here. We are assuming that's reflected wave from the wall, and the incoming wave from the speaker should be able to produce standing waves. So if the standing waves are produced, so she should be able to see the high intensity, low intensity points across where she was walking, not the gradual increase and decrease. There won't be any constant. So evaluate Samantha and Harold's prediction. Okay, so what you can say is question 13. So sound waves travel towards the wall and reflect back. The standing waves will be formed between, well, from the superposition, no? Incoming and reflected waves. Reflected waves. So the positions the sound intensity will be minimum. Because the way that the eardrum recognizes the sound is the vibration. So if you're passing a nodal point, there is no vibration recognized by your eardrum. But if you're going through antinodal points, there is a continuous change. So your drum will vibrate according to that. So that means you will recognize there will be a sound there. But when you're passing a nodal point, there is no change in variation in your eardrum because there is no pressure variation. So because this is a longitudinal wave, a sound wave, because there is no pressure variation at that point, she will recognize those points are the quiet points. So that means, so when Phoebe walks along, she will hear a series of high intensity and low intensity sounds. Towards the wall. So then both are incorrect. So Harold predicted that, what's he saying? Before students, the Samantha is incorrect because the sound intensity will not be constant. As she walks. Not constant. And also mentioned that the other person is wrong because it's not going to be gradually increase and decrease. It's also incorrect because rather it's continuously changing, going up and down. Next part of the question. Are they connected to speakers now? Two identical speakers are set up so that both face the same direction and are connected to a signal generator. Because what they're saying is that your frequencies are same and the amplitudes are same. Phoebe walks in the region in front of the speakers and experiences a variation in sound intensity. She noticed that at some positions she experienced a high intensity of sound, and other positions she experienced the low intensity of sound. At position X, she experienced a high intensity of sound, and at point Y, she experiencing low intensity of sound. Now, she at position X, if you guys looking at it, she's in the middle. So you can assume that the distance from both speakers to X is same. Her path difference looks like path difference is 0. She's like in the middle. Anyway, so she's in a point where producing a constructive interference. At Y, she's in a point where there is a destructive interference. So in terms of answering, you have to say that high intensity as a result of constructive interference, where path difference is equal to, because they're not mentioning this exactly at the center, what we can say in terms of path difference, either 0, lambda, 2 lambda, 3 lambda, and so on. That's why at position X, she's experiencing high intensity. And position Y is a destructive interference where path difference, that means BY minus AY, is equal to either 0.5 lambda, 1.5 lambda, or basically n minus half lambda. So causing a destructive interference. Do you want me to write it on the board, guys? What do you think? So basically you have to say point X, constructive, path difference is equal to n lambda, n equals 0, 1, 2, 3, and so on. At point Y, destructive interference, where path difference is equal to n minus half lambda. Next question. Okay, part B. Just drop it down. At X, constructive interference. Constructive interference, louder sound. So the path difference is equal to n lambda. At Y, destructive interference. There's some quiet sound, what they're saying. Low sound. You get some reflection, so just say low sound. So the reason is path difference is equal to n minus half lambda, where n equals 1, 2, 3, and so on. All right. Part C, the measurements of the distance from each position X and Y to each speakers are. Okay, so they're giving some values. Draw sketch. That's a speaker A. That's a speaker B. And X is somewhere there. And Y is somewhere there. A to speaker X, the AX is 6.6 meters, and BX 5 meters. I think they're giving the wavelength in beforehand. What they're giving, what information? They said that speed is that 20 meters. They haven't given wavelength. Okay. Px that, and then also they're giving AY. So the path difference here, guys, should be AX minus BX, which is 6.6 minus 5 is 1.6. So 1.6 should be a multiple of wavelength. So your wavelength could be 0.8 or could be 1.6. So the path difference is definitely not 0. So that indicates that should be either n lambda. So 1.6 should be n lambda. N could be, can't be 0, should be 1, 2, 3, and so on. The next position is AY is 2.3, BY is 5.1. So the path difference there, 5.1, 2.3. That's a bit of a trial and error to work it out. What's the wavelength here? Could we do question 17? Okay. Yeah. Okay. What's the time? I'll just get this one and then quickly write down 2.8. Path difference is 2.8. Now that should be either 0.5 lambda or 1.5 lambda, 2.5 lambda, and so on. So you need to find one matching for both conditions. Okay, so if I say 0.5 lambda, your lambda going to be double that. That means 5.6. If I say 2.8, let's double check what lambda is possible. Lambda should be either 5.6. Lambda should be either 2.8 divided by 1.5. That should be 1.87. Provide my simplification 5.1, 2.3, 5.8, that divide by 2.5. That's 1.12. Maybe get a bit more. 2.8 divided by 3.5. You get 0.8. So these are the few things. But this situation, if I put n equals 1, the lambda could be 1.6. N equals 1. Lambda could be 0.8. Or lambda could be 5.3. No, that's not right. 1.6 divided by 3. 0.53. So you can see that the one matching there. So your lambda has to be satisfy both conditions at 0.8 meters. They ask you to find the wavelength, right? No, they ask you to determine the smallest possible frequency that the signal generator is emitting through the speakers, and then you use the V equals F lambda. Okay, your frequency. Get that. Because all the other ones, we did not get matching any match here. If you go 4.5, it's getting smaller and smaller. That's the first larger one. All right, that's a trick. Let's quickly do. So you need to do constructive, all the conditions, destructive, all the conditions, and look at the what matching wavelength, and then find the frequency. Okay, question 17, just before we finish it off, question 17, very quickly. What they're saying is, you sending beam of electrons through double slit. If they're purely behaving like particles, what you expect here is a random pattern. Maybe more like particles are hitting here, hitting here. An experiment is conducted where individual electrons of the same kinetic energy are fired one at a time. So you fire one electron at a time. This is where wave particle duality comes in. Once the electron comes in, it just behaving like a wave, so it can go and hit on a random point on the screen. The electron pass to the slit and strike the detector. The detector screen image shows that the electrons strike at a particular position. These positions are regular spacing apart from each other. Explain that the detector screen image in this experiment indicate about the nature of electron involved with this experiment. So what you have to say to start with, when you're shooting electron one at a time, you can see random bright spots. If they're purely acting like a particle, they should go through and hit on certain points. At the beginning, you can see random distribution of bright spots. Over the time, if you let this experiment run, then you can see a clear pattern is emerging. The clear pattern we can recognize as an interference pattern. The interference is a purely a wave behavior, wave nature. So you need to say that. But over the time, a clear, distinct pattern appeared on the screen. On the screen. The bright spots are have a greater probability. Probability to accumulate in some places. Than others. This pattern can be identified as a interference pattern. Interference pattern. Interference is a unique wave behavior. for basically saying that interference is very unique for waves. Therefore, it can be concluded that electrons passing through double slits clearly showing the wave behavior. Demonstrating wave behavior. As long as you targeted saying that the pattern is interference over the time, is where the bright spots are accumulating, the collection of the bright spots as a result of constructive, destructive interference. Maybe just drop constructive and destructive as well. Because some places you get the large accumulation of these bright spots, some places not. The places we are accumulating the constructive. So what you can, because the way that the question is giving, what we can assume is when they in a ground, so open ground, you can have some reflection coming out from some other places. Yeah, the sound is going like a spherically everywhere, not in one direction. So you can have trees, you can have buildings. Ideally, if you can isolate all the other sound from the surrounding, but in the whole question, they say there are nothing else surrounding. Okay, but here the second one is open ground. So open ground, so you can have some reflection coming from somewhere. So that means it's not only the two waves that going to interfere. Some of the waves can travel any direction, right? It's just a point source in the space, a speaker. It's goes spherically everywhere. So it can hit onto a tree or maybe another building somewhere, and then they come back. When they're coming back, they're not going to be in phase. So these sounds can arrive to that point. So that's where they're saying lower sound rather than no sound. So if they want to get around with that kind of question, they can say there are no any other disturbing whatever thing that on the surrounding, on the place. So then you can assume there is no reflection or any other interference coming from that particular location.
Okay, thank you.
Yeah. Okay, shall we stop there, guys? Now, keep in mind, you need to finish this paper. No going back, you have to finish, And then take notes, open up a spreadsheet or Word document or exercise book and reflect back the sections that you have trouble with, sections that you made errors. Make a note, and then that means your 2018 NEET paper, you're done. You're not looking at it, but you get the information from that paper into your spreadsheet or Word document. So you need to improve next time. All right, guys, I'll let you guys go. Okay.
Excuse me, sir. Could you put this online? Because I wasn't able to.
Yeah, sure. When is your SAC?
Okay. It is on Tuesday.
I sent.
I didn't matter.
Did you get the practice material I sent earlier?
It's like the one with like 300 pages or something, isn't it?
Yeah, you don't need to do 300 pages as long as you select two different.
Yeah. I think I got it.
Yeah, you do it.
Yes, so this Tuesday is Latin Matter, and then next Tuesday
You have
there's gonna be on paper waves.
Yeah. Okay.
Thanks,
Yeah,
sir.
pretty much. Yeah. Okay. Okay. See you guys.
Thanks, sir.
Bye. Bye.
Thank you.
Thanks,
Thank you, sir. Bye.
Bye.